Hi everyone, welcome back to Vision Unleashed 10 Breakthroughs Shaping the Future of Computer Vision. I'm your host, Ram Iyer, and this is episode 2 Learning Without Labels, where we dive into the self supervised revolution, how models teach themselves to see. Last episode, we covered vision transformers. Today, we unpack SimCLR, BYOL, two landmark frameworks that learn powerful image features without a single human annotation. Joining me again here, Dr. Sukant Khurana, who's been experimenting with self supervision in both vision and neuroscience. Dr. Sukant, great to have you back.
Thanks, Ram. Excited to share how these methods let us harness the oceans of unlabeled images out there. And I like to sort of be categorical that I have transitioned from being a scientist involved. I'm involved in the sense that I lead teams which are involved. My hands on work has obviously taken a backseat with teams getting bigger and bigger, but happy to be here and share whatever I know.
Uh, Great, sir. So, to start with, can you explain the core idea behind SimCLR?
Yeah, SimCLR treats each image as its own class. You take one photo and generate two different augmented versions. Maybe you randomly crop it, adjust colors, or blur it. Those two views are a positive pair, and every other image in a batch becomes negative. The network learns to pull the positives together in an embedded space and push the negatives apart. Imagine that we have data set of wildlife photos. SimCLR might take a picture of a tiger, crop its face, flip it horizontally to make it one view, and apply slight color shift for a second view. The model learns that both belong to the same tiger feature without ever knowing the word tiger.
Yes, sir. But what about the architecture? How does it leverage standard backbones for its particular cause?
Yeah, so you simply plug a projector head, a couple of small fully connected layers on top of a ResNet 50 encoder. During training, you compute contrastive loss on the projector outputs. When you evaluate, you discard the projector and use the ResNet features for downstream tasks. Let's take an example in industry. A manufacturing line might capture thousands of unlabeled part images. Using SimCLR, you could self-supervise on those raw images and then fine-tune the encoder to spot defects, even if you only label a handful of examples later.
Exactly, sir. So that's a very good example. So, but sir, through practice, SimCLR basically needed a huge batch size, like a thousands of images per batch. So, why do you think, why so much or why so many images in a batch? So,
Yeah, so contrastive learning thrives on diversity of negatives. With a small batch, the model has only few negatives to compare against, which can lead to shortcut solutions. Large batches provide rich set of negative examples, making embeddings more discriminative.
but massive batches strain hardware. So, BYOL or bootstrap your own latent offered a way around that, right, sir?
Yeah, exactly. BYOL pairs an online network and target network both see two augmentations of the same image, but instead of constraining against negatives, the online network tries to predict the target network's representation of the other view. The target network's weights are updated as an exponential moving average of the online network. No negatives needed. There's a practical example. In medical imaging, you might have thousands of unlabeled MRIs. BYOL can learn robust features by simply augmenting each scan, adding noise, simulating artifacts, and bootstrapping against itself. Then, with only a few labeled scans, you can train a classifier to detect tumors.
Yes, sir. And BYOL assured almost the same ImageNet performance as SimCLR, but with smaller batches and no negatives.
374.3 top 1 accuracy on ImageNet with ResNet 50 encoder matching many contrastive methods. but with less compute overhead.
Exactly, sir. That's right. So let's talk augmentations now. These frameworks hinge on choosing the right transforms on the image. So what really matters in that, sir?
Strong, diverse augmentations are crucial. Typically, you use random croppings with resizing, color jitter, Gaussian blur, and horizontal flips. Each transform teaches the model to be invariant to that change, scale, lighting, texture, or orientation. For satellite imagery, you can take like concrete example for satellite imagery. You might add random rotations, simulate cloud coverage, so the model learns to recognize land features whether they're obscured or at different angles.
Exactly, sir. So beyond SimCLR and BYOL, a flurry of follow-ups appeared like Moko, SimSiam, Barlow twins, and right now we also have the masked autoencoders as well. How do they fit in into this, sir?
Great question. So each tackles core challenges, right? Moko uses momentum Q of negatives to keep batch sizes small. SimSiam proves you can collapse freelearn with simple stop gradient. Barlow twins minimizes redundancy between embeddings instead of pushing apart negatives. They all expand the toolbox for self-supervision.
Exactly, sir. So, where do you see self-supervised learning making the biggest impact next, sir? That is in the current scenarios.
Yeah, so I mean, obviously not clairvoyant. I would take an ancient example from when actually I used to do experiments myself. So back in 2009-10, we simply did negative subtraction for larvae, did the work and submitted it, wrote it. From writing to publishing, it took us less than a month, which is the fastest we could do. That was with a graduate student, Ben Kelly, in collaboration with Nigel Atkinson. So that was sort of my first computer vision paper while being a neuroscience student at UT Austin. I was doing a lot of mathematics AI with NYU and cell biology with Northwestern. So that was sort of first application. From there till now itself is like the distance between flying kites to having F-35s. The world has
Yeah,
changed. So obviously predicting future is a bit scary, but I
exactly.
think the future is in specialized domains where labels are scarce, right? But
Yes,
unlabeled data is abundant. Think industrial quality control. In fact, with Donald Trump's initiative to try to bring manufacturing back in US, while the labor costs are high, this is something which is going to see huge application if one has to really bring manufacturing back to US or Europe. It has huge application in wildlife monitoring, right? The labels are scarce, but unlabeled data is abundant. Same applies for personalized healthcare. Also, combining self-supervision with transformers is an up and coming frontier. Models like Dino show that vision transformers can learn from scratch without labels.
exactly, sir. So, before we go, any tips for listeners wanting to try this at home?
Yeah, start with BYOL or SimSiam on a small subset of CIFAR 10 or STL 10. Focus on tuning augmentations and optimizer settings. Use mid-size batch and a single GPU. Once you see meaningful clusters in embedding space, visualize with TSME, you'll know you're on the right track.
Exactly, sir. True thing for a beginner to do. So, a fantastic advice, sir, and thank you again, Dr. Sukant, for guiding us through the supervised way. Join us next on Vision Unleashed for episode 3, Bird Goes Visual, where we'll explore the Mars Roto encoders and how hiding parts of an image unlocks powerful pre-training, much like Bird did for text. So, thank you for listening.
Well,
If
can't
you
wait to dive in. Because
Thanks for listening. If you enjoyed this episode, please subscribe, like, and share with your network. I'm Ramasaya. See you next time. Bye.